So, dear student, welcome to the course number MA415 Algebra, and today we are going to learn the some basic topics. And I already sent you a mail regarding all the details of the course, and we will discuss further if you have any question on 14th of September and live session from 3 to 4. Okay, so let me start with some basic things. So what are the basic topics you should learn in this course, or we should know? Okay, so this is, I'm just giving you a very quick overview of basics. I know that you must have learned this thing in your bachelor undergraduate course. Okay, so the first thing you should learn what is a set. Okay, so you know that, so let me just briefly say that a set is a collection of well-defined and distinct object. Okay, so now you know that there are two properties. One is a distinctness, and one other one is the well-definedness. Okay, so what are, for example, um, distinct means what? So the elements of the set must be all different. For example, if you have a set 2, a collection 2, 3, 4, 3, then it is not a set because you have these 3 repeat here. Okay, similarly distinctness means what? That elements of the collection must be defined properly. For example, if I have a collection, say I'm writing that collection of all large integer, say, again you see that this large is not well defined. Okay, so larger than what? So that is not mentioned here. So this collection is not a set again, right? So the set must satisfy two properties, and none of the properties, if one of the properties is not satisfying, then this cannot be a set. This is only a collection. Okay, now the second property which you should know is a function on a set, or some people also call this mapping or map. Okay, whatever you like to call it, mapping, map, function. Okay, so you define it by this symbol. So if a function from a set x to y, so what does that mean? That means this, so I will write down this is a subset of um, the Cartesian product x plus y. Okay, kind of, what does that mean? That means that you taking an element from x and you are putting an image inside the set y, and this should satisfy these properties. Okay, so satisfying, again, well defined this property. So what is well defined? uh, well defined property. So what is well defined property? So what does that mean? That means, say, so that is, so if, say, suppose we have two elements a and b inside x, such that f of a, the image of that two are different in y, then the objects are also different, then a not equal to b. Okay, see, if the image are different, then object itself are different. Okay, so this is called the well defined property. You can also write down the same thing as this is equivalent to, so this is the symbol if and only if, or equivalent to. Okay, so we use this symbol. So this is also saying that if a implies b, a equal to b, then f of a equal to f of b. Clear? So you can understand that this property is actually kind of opposite property of something called injective property, which you already learn in a function. Okay. So I believe that you already learn those things in your school: injective, surjective, bijective. Okay, those things you already learn. So I'm not going to discuss those things again. This is all basic things. Okay. And another important thing you should learn. Um, so this is, I should say, relation. So so let me write down. So special kind of relation. So you know the any relation on a set, say X. What is that? So this is so this, say, a relation on a set X is a subset of X cross X, right? And you already know there are many such kind of relations. Okay, so reflexive, right? I'm not writing in all the details because this is you have learned in your schools. Symmetric, transitive, okay. And if a relation satisfies all the three property, then this is called an equivalent relation. Equivalence relation. There are many more other relations. There is something called antisymmetric. There is something called asymmetric. And there are many more such things. Okay. And if a relation satisfy uh, one instead of two, if you satisfy four and three, then this is called a partial order relation. These two are very important, so that's why I am writing. Okay, partial order relation. Okay, so this is basic thing you already know. So now one more thing which is important, and so I am assuming here something called ZFC, Jarmelo-Fenkler choice, with Jones lemma. Okay, so what is that? So let me write down Jones lemma. These are all you must have learned in your undergraduate, so I am just going quickly. So suppose we have a set and a partial order. So let X be a set, and you have some relation R be a partial order on X. Okay, so what does that mean? That means R satisfy three properties: R is reflexive relation, R is antisymmetric relation, and R is transitive relation. Okay, so this is the thing. So R satisfies, right? This is the meaning that 1, 4 and 3. Okay, uh, so this is the setup. If you have a set and a partial relation on X, then okay, so then I need to tell what is a chain. To chain of a partial order, so this kind of set is called XR, is called a poset. Now if you have a post set, means a set and a partial order, then you can have a something called chain. Okay, so let me write down the statement first, then I will talk about that. Then, okay, if every chain of X has a maximal element or least upper bound, whatever, maximal element, then X itself has a maximal element. Okay, so what does that mean? So that means that to check the post set has a maximal element or not, it is enough to check that all its chains has maximal element, right? So what do you mean by the maximal element of the set? So it means that um, so what is the chain? The chain is a total order. So a chain. So let me. So, so a chain in a post set is a totally ordered subset of the set of X. Okay. Uh, so what does that mean? Then given any two elements, so you can order them. Either they are one is bigger than another one, or another one is bigger than another one. Okay. So this total ordering should be there. Okay. So if a chain has a maximum element, then that implies Jones lemma tells that is sufficient to tell that the whole set has a maximum element. Okay, clear? So now let me. So what more basic thing we require? So maybe, yeah. So one more thing I should say inside inside the equivalent relation. So it's a note that this is you already learned. Then again I'm writing note that every okay, so equivalence relation every equivalent relation on a set, whatever set, say X, um, forms a partition on X. Partition on X. Okay, so I hope you know the meaning of partition. If not, maybe in the discussion session I will discuss again. Okay, so given a equivalent relation R, so you can have a partition. So you can write down X in terms of this joint union of, this is the symbol of this joint union of X size with some I belongs to some kind of um, numbering set. Okay, can be finite, lambda can be finite, infinite, anything. Okay, so what does that mean? That means you can write, you will have a subsets of X as the union will be X, and this is joint union. So what does that mean? That means given any two such xi and xj, their intersection is phi always. Okay, if I not equal to j, whenever I not equal to j, then xi xj are phi. This two property, if some if a collection xi satisfy this two property, then this collection is called a partition. Okay, Clear? So every equivalent relation forms a partition, and vice versa. If you have a partition on X, you can define a equivalent relation. It's obvious. Okay. So these are basic things. One more basic idea I should tell, maybe five or something, whatever. So this the notion of permutations. Okay. I hope you already know what is permutations from your schools. So let me again define it. So a permutation on a set X is a bijective map. I'm assuming that you know what is a bijective map. Map on X. Okay, so permutations are nothing but bijective maps. So what does that mean? So this is a map from X to X, and it is both injective and surjective. Okay, so this means this is injective or subjective. Okay, so this is the meaning of permutation. Okay, so what does that mean? If you say, give me a set, any set, finite set, let me start with the finite set, then you can define a permutation always, a map from this to this. So for example, suppose you have set, say 1 2 3, and then how many such permutation? Question is that question. So how many permutations are there on A? Okay. So what does that mean? That means you are asking how many such bijective map can be there, right? So obviously you can easily find out. So for example, you may have a map, say F1, uh, and this F1 map actually, what does it do? So it sends 1 to 1, 2 to 2, and 3 to 3. It sends every element to itself, and you check this is a bijective map. Similarly, you can have say F2 map. So what does F2 map do? So it sends 1 to 1, but it changes 2 and 3 itself. So it permutes, it sends 2 to 3 and 3 to 2. Okay. So this kind of, in the first symbol we write down in cycle notation either 1 or 2, whatever. The second symbol we write down by this 2 3. Okay. So by this 2 3 means, see, whenever I am not writing any symbols, say 1, that means that going to itself. But 2 3 means 2 goes to 3, 3 goes to 2, right? Similarly, you can have this third, okay? And here say 1, you are going to 2, and 2 goes to 1 back, and 3 remain itself. And the notation, cycle notation will be what? This will be 1 2. Okay, so these are called cycle notation or cycles. Okay, similarly you can have another map by, say 1 goes to 3 and 3 goes to 1 and 2 remain itself, and obviously this symbol will be 1 3. Okay, 1 3, yeah, this first round bracket. Okay, now you see that there are still uh, two maps left. What are those maps? So let me write down another two maps, say F5, and what is this S5? So it sends 1 to 2 and 2 to 3 and 3 to 1, and in second notation you write down 1 2 3. Okay, Similarly, you have another one, the last one, F6. It's NC 1, 2, 3, 3, 2, 2, and 2, 2, 1. And this is the symbol. In cycle notation, the symbol is this. Okay, 1, 3, 2. And you check that these are the only such permutations on the set of 3 letters. So what does that mean? That means a set of 3 letters has 6 number of permutations. Okay, and there is something called permutation group. I will come there after defining what is a group, and we will see that this collection of permutation, they forms a group under composition. Okay, that will come. And this you check that. So uh, um, these permutations with, sorry, this is not 1 2, this is only, yeah. So permutation with these two elements are called actually uh, transitions. Okay, sorry, transpositions. So these transpositions are very important in our group theory, and you must have learned this transposition in your undergraduate. Okay, so these are the basic idea of permutations and transpositions. Now let me start the one of the first important things in our um, syllabus. So this is called group theory. Okay, so group theory start with something called groups. Okay, so what do you mean by a groups? Groups means I'm talking about many groups together. Okay, so let me define. So say a non-empty set uh, say for example G with a map, say star, from G cross G to G is said to be a group if satisfies the following property. Following properties. What are the properties? So property number 1, and that called associativity. Okay, so what is the meaning of associativity? So what do you mean by the associate property? So it's called, suppose you have okay, so you have say 3 elements, say A, B, and C. So we have right small elements inside G, and you want to perform the operation on AB first and then C, like that. A star B, this will be element of G by this map. Okay, and then again you perform on C, or you can perform the operation on B and C and then perform with that with A. An image of these two both uh, final answer will be same. This is the meaning of associativity. Okay, so what you learned, so it has something called associative property. So always if you start with 3 elements, and if you do first two operation and second one with the third one, and if you do first, second and third and then with the first one, both are same. Okay, this property is called associative property. Associative property. Okay, and so this is first property which one should satisfy, and second thing is something called existence of identity. Okay, so how do I write? So I should write down that um, okay, so maybe so so how to say existence of identity? So given so maybe I should write down that like that there exist okay, there exist okay some element. So let me write down E is the symbol. E belongs to G, and this is called the identity. So I of the group such that it has a nice property such that for any element, so you start with for any A belongs to G, that the operation A with that element E from both sides they are same and they equal to A itself. Okay, so this property is this element is called the identity if this exists also. So this is the second property it should satisfy. Okay, and you have another property is called, so this is called existence of identity. Okay, and then third property existence of inverse. So what does that mean? So uh, so for any element say A belongs to G, you will have there. So this is a symbol for there exist. Uh, 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 yeah. So this means there exist. Okay, this is symbol. Okay, there exists another element B belongs to G, such that what happened? Such that A star B and B star A, whatever which direction you do, you will end up with the identity. Okay, so this is all existence of inverse. Okay, and these are you already learn in your schools. So I need to delete this page. Okay, so now I am fine. So now let me give some example. So the basic example you already learned in your thing. So let me again tell you. The most basic example comes something called integers. Okay, so integers. So these are called integer with say addition. Okay, so what does that mean? That means so these are integers. You have the collection of integers with the addition operation. So addition is an operation. This map z cross z to z. It takes two integers, say n1, n2, and the image is nothing but n1 plus n2. Okay. So you see that this operation satisfy the property. So this is symmetric. So You start with n1 plus n2 and then plus n3. This is equal to n1 plus n2 plus n3. These are obvious things. Okay. Similarly, it has identity. You see that um, uh, the zero element, the identity, right? So given any integer n, you just add 0 from both sides. Ah, you end up with the same element. Similarly, given any integer n, you see that there exists something called negative integer minus n. Says that minus n plus n. This is identity 0. Okay. So this is one example, and there are many examples. You just check that rationals, set of rationals number with addition, real numbers with say addition. They all are groups. Okay, they all are groups. And then you can have many more examples. You can have something called that. Say for example, let me write down say m to say r. What is this? This is collection of matrices A, B, C, D, 2 by 2 matrices, and such that this A, B, C, D are element of real number. Okay, you can instead of R you can have any other proper structure element. So we will define it something called state or so, and you have this with say matrix addition. Okay, so you know how to add two matrices. They also forms a group. You can have something called um, permutations. Okay, so let me just define it. So suppose I have 1, 2, 3 elements, and then some people define it by permutation on x, this symbol, or some people define sx also by this. Okay, so this is what, this is a collection of all those 6 permutation. We already seen that. Okay, so f1, and f1 is the identity element actually, so I'm writing e, and f2, f6. Okay, with composition map of composition operation. Okay, so what does that mean? That means you know the meaning of composition. So if you have some say A compose G, so this is something again map from X to X. Okay, and you can easily check that if F and G both are bijective maps, similarly if compose this is also a bijective map. So this is again a permutation, right? So you have the operation composition, which is a map from um, this Sx cross Sx to Sx. Okay, and it satisfies the all the properties. It has identity and inverse. You check it. This is homework. You check that this forms a group. Okay. Yeah. So these are all basic things. So that's why I'm just going fast. Um, and some property you can one more. Yeah. So these permutation groups. There are very specific kind of permutation groups. Which kind of subgroup of permutation groups, that's also important. So I should say another example is called Okay, so Palmason group also called group of symmetries. It has also a name, group of symmetries. Okay. So, or sorry, it's called symmetric group, not group of symmetries. And there's something called group of symmetries. So that, let me write down that. What was the number? 6 probably. Yeah. So 6 example. It's called trihedral group. Okay. So let me define what is this dihedral. On say n symbol. Okay, it's also called uh, group of symmetries on n symbol. Okay, so what does that mean? So for example, let me start with and proper examples. For example, say suppose when n equal to 4, say n equal to 3 also you can do, but let me start with, maybe start with n equal to 3 itself. Okay, so n equal to 3 means, so we have a trigon. Proper trigon means is equilateral triangle. Okay, so all the sides are equal and these angles are 60 degree. And the question is that um, how many symmetries are there? So symmetries means are what? Symmetries are those which are invariant under rotation and permutations. Okay, so rotation and reflections. Okay, so you can do rotation on some axis or you can reflect on some line. Okay, now you see that if you just rotate, so for example, say let me rotate by clockwise or anti-clockwise, doesn't matter. Okay, so is clockwise you are rotating by 120 degree, so this angle is 120 degree, right? Then you 1 2 and 3, so 1 will come to 2, 2 will come to 3, 3 will come to 1, and then again it will be the same figure, so symmetry will be the same, right? So this will be one element. Similarly, so this is an element and you can just do many times, right? And similarly you can do reflection also. For example, uh, so 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 rotation by say 120 degrees and then 240 degrees and 360 degrees, they are all the symmetric element, right? And this is the identity. In fact, this is identity. And then you have reflection also, right? What will be reflection? So you'll have this, and then say for example on this line. Okay, so you can reflect on the straight lines which passing through the midpoint from here to the top one here, and you see that here the 1 will be 1 and 2 and 3 will be interchanged, right? Clear? So now if you see this element, you check that this group on 3 element is exactly S3. So this uh, so generally on 3 symbols diagonal group people write down by the symbol D to N. Okay, I will also use that symbol D to N. Okay, now you check that D6 is actually nothing but S3. Okay, symmetric group 3 elements. Okay, but this is not true for other cases. For example, what is D8? So D8 means what? So on 4 elements, right? So we'll have uh, square, and you want to know that how many symmetries are there. So you can either rotate or you can reflect, right? So rotate, so there will be 4 elements, and then you can have reflection. You can have deflections with respect to this line, or with respect to this line, or with respect to this line. or with respect to this line, right? So there will be 4 such reflections and 4 such rotations. So total number of elements will be 8. That's why it is called D8. So given a element, given a n gone, so what will be the element? So Dn is what? Dn has 2n elements. So given any n gone, symmetry n gone, then you will have group of symmetries. Number of symmetries will be 2n. And how do you write down this group? So this group will be write down by these symbols that is generated by 2 elements A and B, such that A square equal to identity. So A is the reflection. So when you reflex do reflection with respect to this line twice, then you will come back to the same place, and that is the identity. Similarly, b to the power n equal to identity. So for n many points, if you rotate n many times, you will be the same position. And you will have one more of properties, that a, b. So this is either you can write down by this notation that um, a b equal to b inverse a, or you can write down, okay, so um, yeah, but yeah, so either you can write down by these, or uh, maybe you can write down by a b equal b inverse. This is fine, yeah. Some people also write down by ba equal to a inverse, ba equal to ab inverse also. I mean, simple. Okay, no problem. So any simple. Okay. So and how this will look like? This will be of this form, that so you have identity and then you have a, okay, and then you have b, and then you have b square up to b to the power n minus 1, okay, b to the power n equal to identity, and then you have this product ab square ab cube and so on, and ab to the power n minus 1. You check there are 2 n many elements here, okay, clear. So this is these are called diagonal group of symmetries, and maybe I will stop here for today's lectures. Okay, the first lectures. Okay, so today I have just discussed mainly the basic of algebra which you have learned. Okay, and please feel free to write down your question on the comment section in the YouTube video, so that I can answer your question as soon as possible. Okay, and also we can discuss those things on our live session also, which will be on 14th of February. Okay, so today this is the end of today's video.